Just like I say, this is kind of not planned, but we're just gonna have to make do. So let's take a look at, on your notes from yesterday, there's one more example I wanted to do. We looked, right before we ended the day, we reminded ourselves about how to deal with graphing an inequality, right? Just a regular old linear inequality, right? And this is where we left off. I think we did this one. Yeah. So we just have to graph the line, right? And this is line's easy to graph. The y-intercept is 3 and the slope is 2. But how do we, if it's an inequality like this, what do we do? Well, because we're not using an equal sign here, I would graph the line as a dashed line, so it's only a boundary. And here's the important part. When I have y is greater than the line, that means that I'm only graphing the stuff above the boundary, right? Okay, so we've done a bunch of that. I'm sure you're familiar with that. Okay, how is it going to change for a problem like this when it's a quadratic inequality? Okay, good. So now I'm going to have the boundary still going to be dashed, right? Just like before. Only this time it's not going to be a line. It's going to be a parabola, right? So I'm going to have this dashed parabola. And if I'm graphing f of x or y is greater than the parabola, I'm just going to shade everything above the parabolic boundary. So it's going to be a weird looking region, but it works the same way. All right, so let's do this one, mainly because I want to just review how we graph a quadratic function in standard form. It's a little bit harder one, where a is equal to 1/2, it's a fraction. So let's focus on just the boundary line for a second. Okay, so let's treat this as an equation, and then we'll graph the inequality after we figure out what the parabola looks like. So what are our values of a, b, and c here then? 1/2, okay. Okay, and so if we want to find the axis of symmetry and the x-coordinate of the vertex, we do the same thing for both of them, right? If we want to, let's make this is going to be our vertex, this ordered pair, let's say. If I want to find the x-coordinate, I can just use that formula for the axis of symmetry. I need you guys paying attention. So what's my formula? X equals? Negative b over 2a. And so if I plug those in, if b is -4, what's negative b? 4. Over 2 times a, which is 1/2. What's 2 times 1/2? 1. So I get 4 over 1 equals 4, right? So we end up with x equals 4 is our axis of symmetry. So there it is. And it also tells me that the x-coordinate of the vertex is 4. How do I find the y-coordinate? Plug it in. I just go back to my function and I plug it in. So remember what our method of that is, right? If we want to evaluate a function, every place where I used to have an x, I'm just opening up an empty quantity, empty set of parentheses to dump a value in. In this case, my value is 4. So every place I had an x, I'll plug in a 4. And what's that give me then? I find that f of 4 equals what? Hey, Dylan, why don't you go over there? It's not your fault, but yeah, I just don't want you guys to be together. That's not working. So what's 4 squared? 16 times 1/2? 8. 4 times 4? Plus 12. So I get 8 plus 12 is 20 minus 16? 4. Okay, so that tells me that the y value of the vertex is 4, so we can graph that point. I go over 4 and I go up 4. So there's my vertex, right? Okay. Now all I need is just some additional points, right? An additional point or two, and I can just pick points on one side and reflect them over. I only have to work on one side of the axis of symmetry. So what are some values of x that I could pick? I want to be close to the axis of symmetry, right? If that's at 4, What's the next value I could plug in? I could plug in 2, or I could plug in 3 maybe, or something like that, right? I could plug in x equals 2, or I could plug in x equals 3, or I could go on the other side and plug in 5 or 6. But wouldn't it be easier to use the 2 and the 3 instead of the 5 or the 6, right? Smaller numbers, a little bit, it's not a huge deal, it'd work either way. We might as well work with smaller numbers. Now look what happens if I plug in the 3. There's my function. So if I evaluate the function at 3, I get 1/2 times 3 squared minus 4 times 3 plus 12. So what's that give me? 3 squared is times 1/2. Well, we'll just write it as a fraction. 9 times 1/2, 9 over 1 times 1 over 2 is 9/2, right? I'm just going to multiply 1/2 times 9 over 1. So I get 9/2 minus 12 plus 12. Well, at least the 12's cancel, right? Those add to 0. And I end up with f of 3 equals 9/2. That's not a very convenient number, though, is it? Right? It'd be 4.5. It's not super convenient. I got a fraction out of it. Now, I can put the point there, but it's a little harder than it, what do we say, 4.5? Yeah, I went over 3 and I went up 4.5, so I was right there, wasn't I? That's just not a real convenient one. What if I plug in 2 instead? If I plug in 2, that's going to work better, isn't it? Right? Because 2 squared is 4, and 4 times 1/2 works out nicely. 2 divides into 4. So what do I get? 1/2 times 4 is 2, minus 8 plus 12. So 2 plus 12 is 14 minus 8. So what's f of 2? 14 minus 8. Right? 6. There you go. So we get the point 2, 6. So I go over 2 and I go up 6. That's right there. That's a little better point, right? A little easier to graph, a little easier to calculate. We really didn't even have to probably do that other one, right? It's a fraction. We could have just skipped it. As long as I get 1 point on each side like that, that's probably enough to graph the parabola. Okay, and then we could just reflect those over the axis of symmetry to get points on the other side. And if I connect them, okay, when I connect them, remember that we're actually graphing the inequality. Okay, we just used all this stuff to get the points that we need to create the parabola. But what am I going to do? What do I need to remember about this inequality if it's f of x is greater than? Okay, I'm shading above. And what about the boundary then? Am I graphing the parabola as a solid or dashed? It's going to be dashed. Okay. So we've got something like this. There's my dashed boundary, and I'm going to shade everything above. Which will just look like this. It's going to look a little strange. But it's just going to be everything going up from there, right? It's going to be a strange looking region, but that's it. Okay? All right, so there's quadratic functions in standard form. I want to look at right here. I want to look real quick at quadratic functions in vertex form. That's the stuff we're going to take a quick peek at today. There we go. So let's just fill in some blanks on the notes here. The good news is vertex form, which is the second form of quadratic functions we're going to work with, way, way easier to graph than standard form. Standard form is the hardest. This is probably the easiest. So the vertex form of a quadratic function, that should say function, is f of x equals a. So far it's the same, but here's where it changes. What do you think it's going to be? X minus what squared, if it's in vertex form? No. Think back to what vertex form looked like for an absolute value function. For an absolute value function, that was an h, wasn't it? For an absolute value function, if we graphed it in vertex form, wasn't it just this? It was a times the absolute value of x minus h plus k, right? Okay, that's what it is for the parent function that's an absolute value function. What if it's a quadratic function? The only thing that changes is instead of absolute values, we've got something squared. That's the only difference, but everything else stays the same. So it's going to be a times the quantity x minus h squared plus k. But the h and the k still have the same meaning. The ordered pair hk is the vertex, just like before, right? So when we write a quadratic function in this form, it's super easy to graph because we can just figure out, well, we can look at the function and say, well, what's h and what's k? Those are the coordinates of the vertex. There's no calculating to do. It just tells us right away. And a does the same thing it did before. The axis of symmetry now, we can write more simply. Instead of saying x equals negative b over 2a, which is a little complicated, it's just x equals h, right? It's just a vertical line that goes through the vertex. And then just like it did with absolute value functions, a, which remember is the vertical dilation factor, determines, how much it's been stretched and whether it gets flipped or not. Okay? So vertex form shows the vertex on a quadratic equation with respect to its parent function, and the parent function in this case would just be x squared instead of absolute value of x. Okay? So then you can tell me here, without even talking about this stuff, you can tell me what's going on here. How is that being transformed from the parent graph? If the parent graph is x squared, what have we done here? If we add 9 outside the function, what is that, a, h, or k? K. So what does k do? What's that do to our parabola? Up and down, right? That's the vertical translation. So all this is doing here, in this example, is we're taking our parent graph and we're just going up 9, aren't we? Right, because k is positive 9. What about this one here? Down 2, because k is negative 2. Everybody see that? Let's write that. Here we get k equals 9. K equals negative 2, so we're going down 2. We're going up negative 2, which is down 2. Now, what about this one right here? There's 2 things being done, right? What is the 1/3 doing? Okay, that's dilating it, right? That's vertically stretching or compressing. Well, it's stretching it by 1/3, but if I'm multiplying the heights by 1/3, if I multiply something by 1/3, is it getting bigger or smaller? Getting smaller, so the heights are getting smaller, aren't they? So we're compressing by a factor of 1/3. And then what is k doing? Up 2. So there's 2 things happening. Okay, how about over here? Okay, I'm stretching by negative 2. So if I'm stretching by negative 2, really the negative does what?
It makes it small.
But no, not the 2 makes it bigger, but what's the negative do? The k is negative. Flipped it, didn't it? Right, it flipped it. And That makes sense because we said that yesterday too, right? We said that if, oh, let's see. Yeah. We said yesterday, remember that if A was positive, the parabola opened up, right? If A was negative, it opened down. Well, doesn't that mean it's been flipped? Right? So just like before, A, if it's positive, it's up. If it's negative, it gets flipped. Okay, so then A is doing two things. The fact that A is -2 means it's being flipped and stretched by a factor of 2. What is that inside there? What's the 4 doing?
Over 60.
No, I think I'm making it a little too hard. What is that a value of A or H or K?
H.
It's H. What is the value of H there? 4. Remember, this is a little tricky. It's -4, right? How come?
Subtracted by 8.
There we go. Because H is the number that's being subtracted from X, right? So H is always the opposite of how it's connected to X. So in this case, because it's being added, it's the opposite, and H is -4. So if it's H, that's going to be the horizontal translation. So if it's going in the negative direction, where's it going? But it's H is horizontal.
Right, so right.
So it's going right by -4, which means it's going left by 4, right? H is the amount of the horizontal translation, so it's telling us how far are we scooting in the positive X direction, which is to the right. So if it's negative, it means we're going left by 4. Okay? Make sense? Okay? All right, so let's try a couple quick examples here. I don't want to do that one. Actually, yeah, I can do that one. Oops. There we go. There. Okay, so we're going to graph this thing. Now, you'll see how much easier this is. It's a piece of cake. So this is in vertex form, right? What are the values of A, H, and K? A is 1. And what about H and K? H is 1. K is... Well, look, that tells us the vertex right there, doesn't it? Right, so the vertex is at 1, -5. So it's right there, which means that the line of symmetry goes through that vertex, right? So we know it's going to be symmetrical about that point. And then I don't really even have to, I mean, I could make a t-table here, but I don't have to. I don't have to do that. All I have to do now is I have to think about what A does. So A is going to take our regular parent function for x squared, and it's going to stretch it by 1, which means it doesn't do anything to it. Right? So let's think about what our parent graph looks like for x squared for a second. If I'm graphing p of x equals x squared, what's the shape of a plain old x squared graph? The vertex is at the origin, right? If I go over 1 to the right, how far up do I go? 1. I go up 1 squared, don't I? Right? So over 1, up 1 squared means I go up by 1. I go over 2 and up by 4 because I'm squaring it, right? By 2 squared. So I go up by 4. And then I would just reflect those points over the y-axis. And this is my parent graph shape, right? It just looks like that. So I would take the normal heights and multiply them by 1, which means I don't even change it. So I'd go over 1 and up 1, over 2 and up 4, and reflect those over the axis of symmetry. And get points over here, and then that's my parabola. Way easier, right? Much less to do. So much simpler. Let's try another one. Okay, we'll make this one an inequality, big deal. All we know is we're going to graph a parabolic boundary. It's going to be dashed, and then we're going to shade below it, right? Below the parabola. Okay, so what are the values? Let's look at the equation. Let's forget the inequality for a second. Let's just treat the equation and see what the parabola looks like. If f of x is equal to negative x minus 3 squared, what are the values of a, b, and c? What's a? Negative 1. Everybody agree? Okay, what about h and k? Everybody think about that for a second. What do you think? Dylan, what's h? Right? Because that's the number being subtracted from x. Good. What about k? 0, right? Because there's nothing added to the end. Okay, so 3, 0, that's going to be, we can put that over here if we want to. That's our vertex. So we go over 3 and up 0. Okay, and I mean, I could use the t-table, but it just takes longer to do. If I know that that's the vertex, so here's my line of symmetry. There's the line x equals 3. I know I've got symmetry about this thing, and what's a doing? A is multiplying the normal heights, right? So normally for my parabola, I go over 1 and what? Up 1, right? So normally I'm doing that. Normally I go over 2 and up, no, 4, up 2 squared, so I go up 4. A parabola, it doesn't make a V, does it? It makes a U. So when I go, the further over I go, the faster I'm going to increase my heights. So it bends it up into a U shape, right? Instead of going over 2 and up 2, I go over 2 and clear up 4, so it starts to bend upward. Okay? So that's what the parent graph would look like. But I'm going to multiply all of my heights by -1. So for example, instead of going over 2 and up 4, I'm going to go up 4 times -1, right? I multiply the regular parent heights by a. So So -1 times 4 equals -4. So instead, I'm going to go down 4, and that's where my point's going to be, right? Instead of going over 1 and up 1, I'm going to go over 1 and up 1 times -1, which is down 1. So that's my parabola. Okay? Try another one. One more, and we'll let you go. Oh, and then, so actually on this one, it really wasn't supposed to be connected with a solid line, was it? Gotta have a dash line. There we go. So we're going to do dash line. I guess I need a point there and there. And I'm shading below. So it would have just been something like that. Right? Okay, last one. How about this guy? So we've got, what are our values of A, B, and C this time?
4.
A is 4, or not B and C, H and K. What's H? -1, K equals there you go. So my vertex is gonna be at -1, -7. So -1, -1, 2, 3, 4, 5, 6, 7. So clear down there. Here's my axis of symmetry. At x equals -1. And so what am I going to do to the shape of my parabola? A is equal to 4. So what's that mean? Dilate it by 4. So all of the regular heights I'm multiplying by 4. So instead of going over 1 and up 1, I'm going over 1 and up 4. Instead of going over 2 and up 4, I'm going over 2 and up. No. If I'm multiplying by 4, right, when I'm dilating, I'm multiplying all the heights. So instead of going over 2 and up 4, I'm going to go over 2 and up 4 times A, which is 4. 16. Yeah, right. So instead of this, over 1 and up 1 and over 2 and up 4, we're going over 1 and up 4 and over 2 and up 16. So it's like clear up there somewhere, right? And then I'll just reflect those over to the other side, and I'm going to get a really tall, skinny parabola. Okay. So it's going to look something like, oh, I guess I need to do dash. No, this one's solid, isn't it? Because look, I'm including the equals, so it's solid. There's the parabola, and I'm shading above or below? Above, yeah. So that's it. Okay, get the idea? So this really matches what we did with absolute value functions. The only difference is it's a different paragraph, and everything else is exactly the same. Okay? Well, you don't have much time today, but tomorrow you can work on all this stuff. Yes.